Thank you for this opportunity to present at the Student Conference on Optics and Photonics. My name is Giovanni Volpe, and I will try to convince you over the next 40 minutes that deep learning is a very good idea for microscopy and optical trapping. The usual approach to microscopy, optical trapping, optics and photonics in general is really top-down, which means that one goes from designing an experiment or some theoretical idea, try to realize it and characterize it, and finally succeed, hopefully. This is the approach I have always used in my research, which has been focused on optical trapping and optical manipulation, mesoscopic physics, and active systems. However, recently, an alternative approach has come about. This approach is based on data. It's a data-driven approach that relies on machine learning. Here you can see an overview of different machine learning techniques that go from neural networks, here, neural networks of various kinds, so they are dense neural network, convolutional neural network, recurrent neural network, generative adversarial neural networks. But you should not forget that there are also other possibilities in machine learning, which include genetic algorithms and reinforcement learning, as well as traditional unsupervised machine learning algorithms such as regression and k-means and self-organized maps. If you want a nice recent review we wrote about the field and its application to active matter, but also to optics and photonics, you can look at this article referenced here. The reason why machine learning has become such a big hit recently is really because machine learning very recently managed to classify images in a very, very efficient way. So this is ImageNet. Many of you, I guess, have heard about it. And in ImageNet, the task is the following. There are many, many images, millions of images, and one has to classify them based on their content, like which images have dogs, which images have cats. And if we go back in time, in 2011, computer algorithms managed to get, made 25% of error, roughly, which means that they got a fourth of the images classified wrongly. But if you look forward in time and we go to 2012, we see that this number goes down. The classification error goes very, very quickly down, reaching down to a few percent, like 3–4% in 2016. Now you can see that this increase in precision by deep learning is mainly due to the fact that deep learning started using neural networks, and to be specific, deep learning based on convolutional neural networks. By the way, usually when I give this presentation in person, I always ask the audience to guess, if they don't know already, what will be the accuracy of a human? What will be the error you would make in classifying these images? Well, what's your opinion? The answer is roughly 5%. This means that about 5 years ago, machines became better at classifying images than humans. This is what actually started the deep learning revolution. And as part of the deep learning revolution, people started using deep learning in many different fields, and here I will show how we use it in some projects in microscopy and optical trapping. So I will present a few projects. I will present in detail one project on digital video microscopy, which we did last year. Then I will present 4 more projects very briefly, just to give you a feeling for what kind of applications we can think of in machine learning when applying it to the field of optics and photonics. So let's start with the digital video microscopy. First of all, what is digital video microscopy? Digital video microscopy basically is about identifying the position and maybe the properties of particles in a video. So here you can see a video, a frame of a video of colloidal particles, and here typically what we will do in digital video microscopy is to threshold the image so that it becomes black and white, and then extract the centroids of those white spots, and then maybe reconstruct the trajectories, and from the trajectory we can do a lot of statistical analysis. This is pretty straightforward. You see that this algorithm is pretty simple, and surprisingly, even though it has been around for like 30 years, it's still very widely used and very successful. However, things can get very difficult very quickly. A few years ago, we were doing some experiments, and here you see a video from those experiments where you can see passive particles, these like spherical particles. They are polystyrene microscopic particles, and bacteria moving between them, these bright spots, because they are fluorescent. And we wanted to track both the particles and the bacteria to understand how they interact in this complex environment. The problem is that it was not possible for us to track this with standard algorithm, and we tried very, very hard. We spent a lot of hours and weeks and months trying that. So you can see the problem when you zoom in. If you look at the details, is this a particle or a space between particles? Is this a particle or a space between particles? Not obvious, right? Well, the best we could do was more or less this. This was a lot of work, and you see that it's not a very good tracking, and it's over a very small area. The problem is that, well, it doesn't really work as soon as you move somewhere else on the image, or let alone move it to a new video. This took roughly 1 week of work from one student of mine, very good student and very talented in digital video microscopy, but that's the best we could do with standard algorithm. That's the time in which we thought, why not explore the possibilities of deep learning? So we decided to try. And here I will just show a very simplified picture of deep learning, just to give you a feeling for how it works. So let's say we have an image of a particle as input, simplified, and we want to track its position. In deep learning, what you will do is to convolute it with filters and get a feature map, and do this with many, many different filters. At the moment, the numbers on these filters are completely random. This is what is called a convolutional layer in convolutional neural networks. Then we downsample the feature maps, mainly to reduce the amount of data we have to deal with, and we combine them with what is called a dense layer in neural networks. So a series of neurons that receive an input, the values of these feature maps, and kind of sum them up in a non-linear way. And finally, they give us an output, which is the position of the particle. Again, the connections in this dense layer and with the outputs are completely random at this stage. So what we get at the output, it's a completely random number. So it will tell us, for example, that the position of the particle is here. At the moment, this is not usable to get the position of the particle, obviously, but then what we do is the algorithm that trains the neural network. So we measure the distance between the estimated position and the particle. This is the error, and we backpropagate it. So this practically means we adjust this series of weights in order to make the error a bit smaller, and therefore we need to adjust the previous weights to make the error a bit smaller, and we need to adjust the filters to make the error a bit smaller. This means we get a slightly better result. Of course, we have to repeat this many, many times. Practically means millions of times. And eventually, we will have a neural network that is able to tell us for a given input where is the position of the particle. The neural network we actually used in this work was a bit more complex than this, but let's say in substance is very similar. In this case, we have 3 convolutional layers and 2 dense layers, and so it's much bigger, but the idea is the same. Now the problem arises. In order to be able to use the neural network, we must first train it. How do we train a neural network? Well, we need couples of input images and positions of the particle. The problem is that we cannot get that experimentally. because we don't have them. If we had them, we will not need to have a neural network. So what we did, which worked pretty nicely, was to simulate the positions of the, well, the images of the particles. The advantage of simulating images is that, first of all, it's very cheap. You can have as many simulated images as you want. Secondly, more importantly, you know exactly the position of the particle. So you can really show the network any number of perfectly known examples. So that's what we did, and we trained the network over some millions of images, simulated images, and, well, at that point we had a network that worked perfectly with simulated images, and we were eager to test it on real experimental data. So what we decided to do is to try with an optically trapped particle. So here you can see a particle. This is a video of a physical particle trapped in an optical trap. An optical trap is essentially a focused laser beam, and the particle stays near the focus and keeps on jiggling around the position of the focus because of the Brownian motion. This is what you see here, and you see that the particle is very nice, the image is very good, very easy to track. This is a standard algorithm tracking it, this is DeepTrack tracking it. They both work perfectly. If you look at the trajectories, the one of the standard algorithm and the one of DeepTrack agree perfectly, down to a fraction of a or a pixel. And we can even quantify with the probability distribution the position of the particle. We can see that both DeepTrack and the standard algorithm produce the same distribution, and here you see the fit, which is exactly what we would expect for an optically trapped particle. Even better, we can even measure the autocorrelation function of the particle position as a function of time, and you see that both DeepTrack and the standard method produce the same result, which fits very well with what we would expect. So what we did next? What we did next is to keep exactly the same particle in the same optical trap. We switched off the LED high quality illumination, we switched on an incandescence lamp, and we get this video now. So it's a very bad image because the illumination level is much lower, there is a lot of noise, but it's the same particle, so we know that the statistical properties of this particle must be the same. Well, so this is what the standard algorithm manages to do. You see that it's not really tracking the particle well. DeepTrack seems to do much better. And if you look at the trajectory, well, of course it's a stochastic trajectory, but somehow the one tracked by DeepTrack looks much more similar to the previous trajectory we tracked in absence of noise. Let's go to the quantitative comparison. This is the fitted probability distribution. You see that the standard method doesn't deliver us anything really useful. It's completely broadened. But DeepTrack reproduces their correct probability distribution. Even better, this is the autocorrelation function in time. And well, the standard method produces something that is essentially white noise. You see that there is a huge peak at 0 time and then essentially goes to 0. The small peaks that you see there are 100 Hz due to the electric grid in Europe, which is at 50 Hz, which doubles in intensity to 100 Hz. So it's really tracking the electric grid more than the particle. DeepTrack, instead, reproduces the autocorrelation function. That's great. And the reason why this is great is because this tells us that subsequent frames are tracked correctly. DeepTrack is not trained to track things in time, but still manages to reconstruct the time behavior of the particle much better than the standard algorithm. Well, this was all very nice, so we decided to apply it to our original problem, and we can see that we could track the particles very, very well. And even better, we could even train the neural network to track also the bacteria and distinguish them. So it really worked very nicely. And then, you know, once you have done a work, you submit a paper, and well, you're happy, you submit, and then it comes back from the referee, and the referee tells us, yes, it's all nice and well, but we would like to see an objective comparison of your algorithm to something that, to some test that you don't make up yourself. And therefore, we decided to compare it to this paper, the methods employed in this paper. This is a paper called Objective Comparison Particle Tracking Methods, in which like 20 groups from around the world came together to compare the performance of their methods in particle tracking. So this is one of the tasks that were given in this paper, and you see that essentially here it's about tracking the position of particles for different densities of particles and different signal-to-noise ratios. And here you see the various methods, and you see that on the y-axis we have the error, and on the x-axis we have the signal-to-noise ratio. Of course, the error gets lower when the signal-to-noise ratio gets higher, and of course the error gets generally lower when you have low density compared to high density, because the particles are more easily distinguishable. But you see, the interesting thing here is that you can see a lot of methods, and of course here they are not identified, the various methods, but no method managed to be best in all cases. With DeepTrack instead, we get that DeepTrack managed to be better than all these methods in all cases. And you see that this is not negligible, because here it goes from an average error of like 2 pixels to an error of 1 pixel, which is pretty good. Here you see that improves from almost 1 pixel of error to less than half a pixel of error. So it's a very big improvement. So we were very happy. We resubmitted the paper. It was accepted and published last year. And what is also nice to say is that DeepTrack is completely free. So we made a nice software package that you can access in the Soft Matter Lab GitHub page. And even better, now we are about to release a second version of DeepTrack, which will be much more powerful, and even with graphical user interface for Mac and Windows. So I really encourage you to have a look at that. It will come out in weeks at this point. Hopefully this week, maybe next week, but let's say in the following few weeks. And again, completely free and very powerful software to apply deep learning to quantitative digital microscopy. Okay, so I spent quite a lot of time on this first example because I wanted to really give you a feeling for a complete project. Now what I would like to give is more a quick overview of other projects we have done with deep learning, and just to give you a feeling for possible application. Maybe something comes to your mind and you decide that you also want to use deep learning in some of your research. So first thing is measurement of anomalous diffusion. I guess all of you know about diffusion, Brownian diffusion. You know, Brownian particles jiggle around because of thermal motion, and they have a very characteristic exponent, while anomalous diffusion occurs whenever there is a system that is probably out of equilibrium or hindered in its movement. So you can have subdiffusion or superdiffusion, and this relates to the mean square displacement of the motion. So here you can see that we have standard Brownian diffusion is the central case, subdiffusion when the exponent is lower than 1, and superdiffusion when the exponent is bigger than 1. These are the corresponding trajectories, and the standard method obviously is to calculate the mean square displacement and fit the exponent. What we proposed was to use instead recurrent neural networks. I will not go into the details of what the recurrent neural networks are and how they work, but what we can see here is that when we have very short trajectories, like 32 points, neural networks are slightly better than the mean square displacement. And of course, when the trajectory gets longer and longer, they become comparable. And here you can see an extensive comparison between the exponent estimated using mean square displacement and the one estimated with the recurrent neural networks, and you see that they fit pretty well. These are various experimental cases, so you see that there is a good agreement, so it works. This is nice, but the idea is never to use deep learning or machine learning in general to do something you could do with other standard methods. You always want to use deep learning to do something that you could not do otherwise. And in this case, for example, we decided to explore some more challenging situation. For example, here, instead of having a uniformly sampled input trajectory, we have a non-uniform sampling. Well, then there are no standard methods that can do that, but with deep learning, we can calculate the value of the exponent of an anomalous diffusion, even if the trajectory is not sampled at regular time. Think, for example, experiments with the fluorophores that might blink. You might not be able to acquire a regular sampling. Another example that is even more interesting is when you have a time-varying anomalous diffusion, so a particle that changes the exponent over time. Here you see that it goes from super diffusive, the blue portions of the trajectory, to subdiffusive, the orange portions of the trajectory. There are no standard established method to find the switching point or to characterize such a trajectory, but the recurrent neural network can be trained to recognize the value of the exponent time by time, and it does it pretty well, and the switching point between the two exponent behavior. So this works also very nicely. So you see, we can do something more than what we can do with standard methods. And also in the case of anomalous diffusion, in case you are very interested in that, we have created a competition organized in collaboration with several groups, the group of Maciej Levenstein in ICFO, Carlo Manzo, University of Vic, Miguel Garcia Mac, Polytechnic University of Valencia, and Ralph Metzler, University of Potsdam. And this is a very nice challenge where more than 50 groups around the world are competing to see who can find the best way to determine properties of anomalous diffusion. We just moved into the second phase on the 14th of September, so you are still on time to join if you're interested. And there will be a very nice competition and finally a very nice workshop in which the winners of the various tasks will be invited. Well, if you're interested, have a look at that. Okay, so let's think of another example in which we might make use of deep learning. So let's go to the simulation of optical forces. So optical forces arise, for example, in an optical tweezer, we use a laser beam, focused laser beam, to trap a particle. And optical forces arise because of the interaction between the incoming field and the particle and the scatter field. Now, the problem is that if you want to calculate them, it's very difficult because we need to calculate exactly the scatter fields, which is a very complex problem. You can imagine why. The particles we want to trap are often in the range of microns, which is exactly the range of the optical wavelengths we use. So we are in the regime in which we have to exactly solve Maxwell's equation for objects that might not be very regular. That's very difficult and time consuming. This is just to show you the equation. So we will have to calculate the electromagnetic field and then calculate essentially Lorentz force with a tensor and then integrate. It's a very expensive computationally process. So what we thought was to instead use neural networks. And here I will show you, So to use a neural network, so to train a neural network to reconstruct the optical forces. How does it work? Well, we input the position of the particle and we get the neural network to calculate the output, the force that the particle is experiencing in that position. Now, here you can see two graphs. This graph shows the error of the method. So you see that the neural network does much better, well, obviously, than the harmonic approximation, where you say the optical trap is just a spring. So it's minus kx, where k is the stiffness constant and x the position of the particle. That does very bad in terms of error because, well, the trap is not perfectly linear. But you can see that you can imagine using interpolation schemes of different sorts. But even the interpolation schemes you can think of do worse than the neural network by a few orders of magnitude. What is even more interesting is that the neural network is very fast. The neural network is basically as fast as interpolation schemes, even though much better in terms of error, and 4 orders of magnitude faster than making an exact calculation of the forces. Again, why do we care about this? Why do we want to have a fast calculation of optical forces? Well, the reason is because this permits us to go and simulate situations that we could not simulate before. As a simple example, think of an optically trapped particle in an optical trap, and which is a droplet that is slowly dissolving, which means that its radius and refractive index are changing over time. And therefore we have 5 degrees of freedom. So we have the position of the particle, x, y, and z, plus radius plus refractive index. Now, let's imagine that we have a flow and we want to calculate how this particle escapes from the flow. Well, to do with the T-matrix, it will take years for the computer to calculate it. So, if we want to do that, but we can do that with the neural network. So, using the neural network to simulate this problem, then we can see that if the droplet dissolves very fast, this is the kind of pseudo probability distribution, so that the droplet will escape relatively fast. If the droplet dissolves more slowly, the droplet will be trapped on the edge of the optical twister for a while before escaping. So we can see this in simulations that we will never be able to do within a reasonable amount of time using the exact theory for the simulation. So again, an example where we can use deep learning to do something more, something we could not otherwise do with standard methods. Okay, to go to a third example, we can think about characterizing microscopic force fields. The problem here is that you might have a Brownian particle moving a force field, and by the Brownian motion of this particle, you want to calculate or know what are the parameters of the force field. There are plenty of methods to do this in simple situations, like for an harmonic optical trap. But there are situations that are more complex and not easily manageable. For example, imagine this situation where we have a particle trapped in an harmonic trap, which is weak in the blue regions and strong in the red region. So basically switches between weak and strong repeatedly. The trajectory might be this one. This is a simulated trajectory. By the way, here we have a very big difference between the weak and the strong trapping stiffness constant. This difference can be also smaller. Well, if I give you this trajectory and ask you to tell me the value of the stiffness constant and the period of the switching, would you be able to do that? Maybe, but you would have to come up with a method to do that, which will require time, ingenuity, and effort. With recurrent neural network, we can get that done in a very systematic way, essentially by training a neural network on simulated data and then applying it to experimental data. And you see that it works very, very well, because we can essentially calculate perfectly the low stiffness constant, the high stiffness constant, and the period of the switching. Again, neural network deep learning permits you to do something that would not have been easy to do otherwise. As a final example, I would like to show you a very recent work in which we employ deep learning to help in the characterization of nanoparticles. Well, you know, nanoparticles are very important in many fields. So they are very important, for example, in food industry, because they are used to engineer essentially the properties of the food that you buy in any supermarket. They are very important for environmental purposes because, well, we need to track where nanoparticles go, and we might want to take a sample of water and be able to characterize what nanoparticles are there. So characterization of nanoparticles is very important. What we proposed very recently is to use a combination of deep learning and holographic microscopy, where we acquire an hologram of nanoparticles, we transform it, track the particles, and finally use the images of these tracked particles with a neural network in order to extract their radius and refractive index. And the beauty of this is that we can do it very reliably and very quickly. So here you see that deep learning approach and the standard approach. And you see that as a function of the number of images, time steps we acquire and we analyze, we see that the deep learning approach within 1 or 2 frames is able to tell us essentially perfectly the radius. With the standard approach, we need many more time steps. Why is this useful? Well, this is useful because you can imagine, for example, having a microfluidic chamber like we do, in which we flow liquid with nanoparticles and we record them for a few frames. So we don't have an infinite amount of frames, and we want to do this as fast as possible to be able to characterize as many nanoparticles as possible. And by the way, you can see that if you do this on many nanoparticles, you see that the deep learning approach gives us exactly, very precisely, the value of the nanoparticle radius, while the standard approach gives us a very broad distribution, this gray histogram. Again, we can do new stuff, we can think of new applications and faster applications thanks to the application of deep learning with microscopy. Okay, so to conclude, I tried to convince you that it's worth looking into using deep learning for microscopy and optical trapping. And I tried to convince you with some example, discussing in depth one example on digital video microscopy, and then a bit more briefly some more recent work we have done. I would suggest you think about possibilities of using deep learning in your research. Always try to think, obviously, whether deep learning is really the best way to go. If you can do something with standard method, you should not look for deep learning. But deep learning can maybe allow you to do things that you will not have imagined possible before. And with this, I would like to just advertise a conference we organize every year. This is the previous year. So it was last August in SPA Optics and Photonics, which should have taken place in San Diego but was online. But we will have a second edition of this conference next year, organized hopefully in person in San Diego, and I really welcome you to look into that. If you are interested in these topics comprising optical computing, AI-enabled photonics, biomedical optics, microscopy, neural connectivity, brain imaging, please look into that if it's of interest for you. I could not put the one of 2021 because we have not yet finalized the program committee, so I don't really know who is going to be there, but the conference chair will be there. And finally, this is a picture taken pre-pandemics of my group at the University of Gothenburg, as well as the various funding sources that have given us money to do the research we love to do. Thank you.